Hello, everyone. So, we're going to continue on talking about factors that affect solubility. Another factor that can affect solubility, especially when we're talking about enhancing solubility in water, is to increase the number of polar groups that a substance contains. So, remember, a polar group is just meaning that we have a dipole that's present. So let's say we look at two different examples. First one I have is cyclohexane, which is just C6H12. So we can see here that all of the groups that are attached to the carbons are all just hydrogen. So since there's no polar groups that are attached to this, this would be insoluble in water, because if this would be a non-polar molecule and water would be a polar molecule, remember we said likes dissolve likes, so cyclohexane wouldn't be able to dissolve in water. But we can compare this to a substance like glucose, where we have 5 different groups here that are polar groups, and specifically we have our OH groups. So because we have the presence of these extra polar groups here, that's what makes glucose very soluble in water, because it's enhancing that ability to hydrogen bond with the water molecules. We can also talk about how we have fat-soluble vitamins, and that's different than our water-soluble vitamins. So vitamin A is soluble in non-polar compounds. So that would be like non-polar solvents or in some type of like fatty tissue, so fats. The specific fat-soluble vitamins are vitamin A, D, E, and K. So those 4 vitamins, A, D, E, and K, are stored in the body, and we do not need to eat these in a really large amount, because for the most part, we do a pretty good job, our bodies do a pretty good job of storing them. But they're different than vitamin B and then vitamin C, which are soluble in water. And these aren't stored readily in our body, and that's why it's really important for us to eat vitamins B and C every single day, because we need them to function since we don't store them readily. If we look at the 2 molecules, vitamin A and vitamin C here below, we can see that vitamin A, which is soluble in nonpolar compounds, remember, so this would be fat, it only has this one polar group that interacts with water versus the rest of the molecule, which is this huge nonpolar chain. So I would only have London dispersion forces that would be acting in that chain, so that is going to overtake this one little tiny polar group that's interacting with water. But this is different from vitamin C, which we can see has lots of polar groups here that can interact with water. So we could see that maybe dipole-dipole or hydrogen bonding could be responsible for vitamin C being soluble in water. Okay, so on the first question it says, predict whether each of the following substances is more likely to dissolve in the nonpolar solvent CCl4 or in water. So we have 4 different substances here. We have C7H16, we have Na2SO4, we have HCl, and we have I2. So we know that carbon tetrachloride would be our nonpolar. So remember, let's follow our rule that likes dissolve likes. So since carbon tetrachloride overall is a nonpolar molecule, we want to find another substance that would be nonpolar to dissolve it in carbon tetrachloride. So C7H16, we've talked before that our carbon-hydrogen bond is a nonpolar bond. So this entire substance would be a nonpolar substance. So C7H16 would most definitely be nonpolar. So if this is nonpolar, it will dissolve in CCl4. Okay, let's move on to Na2SO4. Now, Na2SO4 we know is ionic. So if we have some type of ionic salt, then we can think about those ions could dissolve or dissociate in water. but they probably wouldn't be able to do anything in a nonpolar solvent. So we would say that our ionic compound, Na2SO4, is going to be able to dissolve here in water. My next one, HCl. Now we know that HCl is going to have a dipole, and that dipole will move towards chlorine because chlorine is more electronegative. So because it has a dipole, because then it has a polar bond with it, I would say that HCl is also going to be more likely to dissolve in water. My last one, I2, so I have diatomic iodine here. We know that any diatomic is held together by dispersion forces, and since it's held together by dispersion forces, it doesn't have a dipole instead, or permanent dipole. Instead, it has the London dispersion forces, so it makes it a nonpolar substance. Thus, CCl4 is going to be the best solvent to dissolve I2. Okay, the next question says, arrange the following substances in order of increasing solubility in water. Now remember we said that the more polar groups that we have in terms of adding it to a substance, the more that we can enhance or increase the solubility of a substance in water. So let's look at these different ones. So on this one, I see we have no polar groups. On this one, we have one polar group, which is that OH group, so that's a good polar group to have because we can have hydrogen bonding with water. On this one, we have two polar groups, and specifically, again, that OH group, so that would enhance that even more. And in this molecule, we have still a polar bond here, this carbon chloride bond. And if we were to rank these then of increasing order and solubility in water, I would say that this one would be the least. So I would put this one first because it doesn't have any polar groups. So it's not going to be very soluble in water, if at all. The next one that I would say would be this one. And that's because this carbon chloride bond, while it may have a dipole, it's not going to be as strong as the OH groups because I can't hydrogen bond between this carbon chloride bond in water, versus these two, because of the OH groups, I will be able to hydrogen bond, which will increase the solubility of that substance in water. So I would say this one first, this one next. This one would come third because I only have one OH group here. Then this one must be the one that would be the most able to be increased in terms of its solubility in water because I have two OH groups present here. So just like we can talk about dissolving a liquid in another liquid, just like we can talk about dissolving a solid in a liquid, we can also dissolve gases in solution. So in general, the solubility of gases in water will increase with increasing mass. We can see here that in table 13.1, I'm starting off with N2, and then ultimately, as we move down the column of gas here, we're increasing that mass, and we can see that as the mass is increasing based on the type of gas we have, the solubility in water is also increasing. So typically the reason that we see the solubility of gases in water increasing with increasing mass is just because larger molecules have stronger dispersion forces. Typically, when we talk about the solubility of liquids and solids, it typically doesn't change very much in terms of pressure. But when we're talking about solubility of a gas in a liquid, then we say that the solubility, or we have found that the solubility of a gas in a liquid is directly proportional to its pressure. So we can see that here in the graph to the left. So as our partial pressure of our gases increase, so helium, nitrogen, carbon monoxide, oxygen. So as we increase the partial pressure of a gas, above a solvent, then I can see that the solubility also increases. Or we could say it vice versa. The solubility of any gas in any solvent, if we increase that, then we also know that the partial pressure of that gas will also increase as a result. Okay, so let's say that, for example, we have carbon dioxide that's distributed between the gas in the solution phase. So let's say that starting off here in this example, I have my carbon dioxide gas molecules, and I have some that are here in the solution, and then I'm also going to have some carbon dioxide molecules that are exerting some type of partial pressure above that solvent with the carbon dioxide gas molecules present in there as well. So right now they're just at an equilibrium. But let's suppose that we exert a greater pressure and then we compress. So we're going to exert a greater pressure, and we're going to do that by compressing the gas above this solution, this solvent here. The solvent that contains the carbon dioxide particles that are dissolved. If I do that, if I compress or increase the pressure of the gas above the solution, we're going to force more of these carbon dioxide molecules to dissolve in the solution. So I have more carbon dioxide molecules that have dissolved in the solution. So before we had just 3 molecules here. In this case, we have 4 carbon dioxide molecules. So the reason that we're going to get this, after we exert this greater pressure, the reason we're going to see more CO2 dissolving is because the rate now at which these gas molecules strike the surface and enter that liquid phase has now increased. So because of that, the solubility of the gas is going to increase, and it's going to do that until we can restore that equilibrium. So because we've forced more CO2 to dissolve by increasing the pressure, solubility will also increase. And then once that does that, equilibrium is going to try to happen again based on this new pressure. So now we can see that we have even more carbon dioxide molecules that are dissolved. This is how we make soda. So any type of carbonated drink is made to be this way. We can get more carbon dioxide to dissolve in our soda if we continually increase the pressure above that solution, forcing more carbon dioxide to dissolve, and that means then the solubility of that solution is also going to increase. So we have a relationship between pressure and gas solubility, and that relationship between pressure and gas solubility is expressed by a mathematical formula called Henry's law. So in Henry's law, we have S sub G equals K times P sub G. Now, S sub G is just expressed as molarity. So Sg is simply molarity. And we know that molarity is just our unit capital M. K is just a proportionality constant. That proportionality constant is given to you down here below. So K equals this 3.4 times 10 to the negative second moles per liter atmosphere. And finally, Pg, or P sub G, is just the partial pressure of the gas above the liquid. So typically, let's say if K is measured in atmospheres, our partial pressure should also be measured then in atmospheres. And if it's not, we're going to have to do some type of pressure conversion. Now, the problem here that says to calculate the concentration of CO2 in the soft drink, someone remind me that this is what I'd like to start off with on Tuesday in class. So this slide, this is the problem that we'll start off together with on Tuesday. Okay, so if we look at temperature affecting solubility, And if we think about them in terms of solid solutes in a liquid solvent, then we can see here by this solubility curve that generally the solubility of a solid solute in a liquid solvent will increase as temperature also increases. We do, though, see some exceptions to this rule. So, for example, I have a Ce2SO43. So as we increase temperature, we actually see a decrease in solubility. So we do see some exceptions. If I look here at NaCl, it's a very, very small increase. It's an increase nonetheless, but it's very, very slight. And the rest of them, though, looks like, so KClO3 increases, K2CR2O7 increases. So we can see an increase in most of them, but there are, just so you are aware, a few exceptions to that general rule. So while we said that solid solutes in a liquid solvent increase with increasing temperature, we actually see the opposite to hold true in terms of gases. We can actually see this in everyday life by thinking about carbonated soft drinks. Are usually more bubbly if they're stored in the refrigerator. So we actually see more carbonation if the temperature is colder for a pop or soda. If we're looking at our graph here to the right, we can see that as temperature is increasing, the solubility of the four gases is decreasing. Another real world example would be warm lakes typically have less oxygen that's dissolved in them than cooler lakes. Okay, so the next few slides have to do with ways of expressing concentration. We know that concentration can be expressed qualitatively or we can express it quantitatively. So usually when we express it qualitatively, we use the words either dilute or concentrated. But when we talk about concentration quantitatively, then we can think about it several different ways. So one way that we can express concentration quantitatively is through the mass percent. Let's say that I want to find the mass percent of A, so just some solute that's in a solution. So I would do that by taking the mass of A in solution and divide it by the total mass of the solution, multiply it by 100 to get the percent, thus giving me my mass percent. Oftentimes we use parts per million or parts per billion, especially when we're thinking about something that's toxic or carcinogenic. The acceptable maximum concentration of toxic or carcinogenic substances we report in parts per million, which is ppm, or parts per billion, which will represent as ppb. It shows you this is the same thing as a mass percent. The only difference is that what we're multiplying by. So parts per million is just the mass of A in solution divided by the total mass, but we're going to multiply that by 10 to the 6th. So that crazy thing here off to the side, sorry about that guys, should say times 10 to the 6th, not times 106. And then down below, if we're talking about parts per billion, then we know billion is just 10 to the 9th. So we're going to take the mass percentage of A, so mass of A in solution, over the total mass of the solution, and then times that by 10 to the 9th, which would be parts per billion. We have done mole fraction in the past. So if we're talking about mole fraction, and specifically we'll just say the mole fraction of A, that would be the moles of A divided by the total moles of all components. So there's not very much difference between mass percent and mole fraction. The only real difference between the two of them is that one is using mass and the other one's using moles. In some applications when we use mole fraction, one needs the mole fraction of the solvent, not just the solute. So we have to make sure that we're adding up or thinking about the correct quantities. And we're AP chemists, so we can do molarity in our sleep. Molarity is equal to the moles of solute divided by the liters of that solution. Guys, the last way that we can express concentration is called molality. We'll symbolize that with a lowercase m. Your AP curriculum says that you don't need to be tested on molality, but you're still going to learn it because in college you're still going to have to measure molality. So molality is just moles of solute over kilograms of solvent. Sometimes we find molality better to use than molarity because molarity can change with temperature, and that's just because volume, we know that molarity is moles over liters, so molarity has something to do with volume. And if we have a change in temperature, then the volume could possibly change. So that could throw off the molarity of a solution that we may have measured. But molality is not temperature dependent because moles and kilograms are never going to be able to really change with temperature. So molality can actually give us probably a more accurate measure, even though we use it less frequently. We still need to know what molality is and how to calculate it.